A black hole, by definition, is the one object in the universe that cannot be seen. That's not poetry. That's physics. Nothing, not light, not radio waves, not anything, can escape its gravity once it crosses a certain point. So if you can't see a black hole, how did a team of scientists in 2019 hand the entire world a photograph of one? That photo, the glowing orange ring sitting on a field of pure black, was everywhere. Front pages, late night shows, memes within hours. But almost nobody talked about how it was actually taken, and the real story is stranger than the photo itself. It involves a telescope the size of planet Earth, half a ton of hard drives that were too big to send over the internet, and a team of scientists who didn't even trust their own results, until they tried to break them and couldn't. This is how you photograph the unphotographable. Let's start with what a black hole actually is, because the name is a little bit of a trap. A black hole isn't a hole, it's the opposite. It's an obscene amount of mass, crushed into an impossibly small space, generating gravity so strong that it warps the fabric of space itself. Past a certain boundary called the event horizon, gravity wins completely. Light goes in, light does not come out. So here's the paradox the scientists were chasing. If a black hole emits zero light, there is, in theory, nothing to photograph. It's a perfect void. But a void next to something is still visible by its absence. Picture a black hole surrounded by superheated gas and dust, spiraling inward, getting ripped apart by gravity, glowing white hot just before it crosses the point of no return. That glowing material does emit light, and right at the center of that glow there should be a perfect dark circle, the silhouette of the black hole itself, where the light behind it gets swallowed. Scientists call this the shadow. It's not the black hole, it's the hole-shaped gap the black hole leaves behind in everything around it. That's the target. That's what the photograph was actually trying to capture. Not a black hole, but the absence of one, outlined in fire. The boundary you'd actually be looking at, the event horizon itself, is even smaller than that shadow, roughly 2.5 times smaller in fact. The shadow is the closest thing to a picture of a black hole that physics will ever allow. Out of the hundreds of millions of black holes scientists believe exist in the observable universe, why did they pick this one? A black hole sitting in a galaxy called M87, about 55 million light-years from Earth. Distance alone should have ruled it out. 55 million light-years is absurd. But here's the trick. The apparent size of a black hole's shadow depends on its mass, not just its distance. And the black hole at the center of M87 is not a normal black hole. It's a supermassive black hole with a mass roughly 6.5 billion times that of our Sun. It's one of the largest black holes ever measured, so even from 55 million light-years away, its shadow appears, just barely, large enough in our sky to attempt to photograph. There's a second feature that made M87 the perfect subject. This particular black hole is famous for blasting out a jet of charged particles, traveling at close to the speed of light, stretching out for thousands of light-years from its poles. It's one of the most active, most violent black holes we know of, which made it an obvious priority target the moment astronomers started asking, can we actually photograph one of these? So the target was locked, M87. Now came the impossible part, actually building something capable of seeing it. Here's the problem nobody could get around. M87's black hole, despite being billions of times more massive than our Sun, appears so small and so far away that you would need a telescope roughly the size of planet Earth to resolve it. You cannot build a telescope the size of Earth. So scientists did the next best thing. They faked one. The project was called the Event Horizon Telescope, or EHT. And despite the name, it isn't one telescope. It's 8 radio observatories scattered across 6 different locations around the globe: Hawaii, Arizona, Mexico, Chile, Spain, and Antarctica's South Pole, all pointed at the exact same target at the exact same moment for several nights in April of 2017. This technique is called Very Long Baseline Interferometry. Here's the simplest way to think about it. Instead of building one giant mirror, you combine the data from many smaller telescopes scattered across the planet and use the rotation of the Earth itself to fill in the gaps. Mathematically, it behaves as if you'd built a single dish with a diameter equal to the distance between your farthest apart telescopes, in this case nearly the diameter of the Earth. The resolution this produces is almost absurd. Scientists later described it as being sharp enough to read a newspaper headline in Paris from a sidewalk cafe in New York. But there's a catch with this technique, and it's brutal. Those 8 telescopes aren't connected to each other. Not by cable, not by internet. They're independent stations, thousands of miles apart, all listening to the same target. For the data from all 8 to be combined into a single image later, every single observatory needed to record the exact same fraction of a second with mind-bending precision. The solution was atomic clocks, specifically hydrogen masers, instruments so precise that they barely drift even over millions of years. Every EHT station ran one, silently timestamping every fragment of data down to a level of accuracy almost impossible to comprehend. And then came the part nobody expected to be the hardest, getting the data home. Each telescope was recording around 350 terabytes of data per day. Across all 8 stations, over multiple nights, the total came out to roughly 5 petabytes, more data than several major streaming platforms store in total. There was no internet connection on Earth fast enough to move that much data in a reasonable time. So the team did something almost comically old-fashioned. They wrote the data to helium-filled hard drives, racks and racks of them weighing about half a ton combined, and physically flew them on airplanes to 2 processing centers, one at MIT in Massachusetts, the other at the Max Planck Institute in Germany. One scientist on the project put it bluntly afterward: there is no internet connection that can compete with 5 petabytes of data on an airplane. And then there was the South Pole problem. The South Pole telescope had captured its share of the data, but Antarctic Station shut down for the winter, with 0 flights in or out from February until October. The hard drives from the South Pole sat frozen in storage for months, waiting for the first cargo flight of the Antarctic summer before they could even begin the journey home, through McMurdo Station, then New Zealand, then finally to the United States. It would be nearly 2 years between the moment that light from M87 hit those telescopes and the moment a human being finally saw what it had captured. Here's the part that surprises most people. There was no single click of a shutter, no raw image file. What the EHT actually captured wasn't a picture. It was an immense pile of radio signal measurements that had to be mathematically reconstructed into something resembling an image. This is where the team did something unusually careful, almost paranoid. Instead of trusting one method to turn that data into a picture, they split into multiple independent groups, each working without communicating with the others, each using a different imaging algorithm and a different analysis pipeline on the exact same raw data. The idea was simple. If a black hole really was there, every team, working blind, with no knowledge of what the others were producing, should land on roughly the same image. If it wasn't real, if it was some artifact of one particular method or some hidden bias in the data processing, the results should look completely different from team to team. When the teams finally compared notes, the results matched: a bright ring, a dark shadow in the center, enhanced brightness on the southern side, the same basic structure again and again, regardless of which independent process had been used to extract it. That convergence, multiple teams, multiple methods, the same answer, is the actual reason scientists trusted the image enough to publish it. Not because one telescope took a picture, but because reality kept showing up no matter how many different ways they tried to find it. So back to the question we opened with, how do you photograph something defined by the fact that it cannot be seen? You don't, not directly. What that famous image actually shows isn't the black hole, it's the shape of the absence it leaves behind, drawn in the light of everything it's destroying around it. It's a photograph of darkness, defined by everything surrounding it. It took 8 telescopes on 6 different sites across multiple continents, perfectly synchronized down to fractions of a second by atomic clocks, recording 5 petabytes of data that had to be flown, not streamed, across the planet on physical hard drives. It took independent teams working in isolation just to make sure nobody was fooling themselves. And at the end of it, after nearly 2 years of data sitting in cold storage and supercomputers, humanity finally had proof, in the form of a picture, of something Einstein's equations had predicted over a century earlier but no one had ever seen. There's another black hole sitting at the very center of our own galaxy, Sagittarius A star, the supermassive black hole at the heart of the Milky Way. It's far smaller than M87's, but it's also far closer to us. And in 2022, the EHT team turned their planet-sized telescope toward it too. What they found was even stranger. That's a story for next time.